Hello everyone, thanks for watching this video. I'm Yin from Peking University. I would like to present our work accepted by ACL 2020 on the robustness of language encoders against grammatical errors. This is a joint work with Quanyu from Shanghai Jiaotong University, Meng and Kai-Wei Chang from UCLA. This work is done while Quanyu and I interned last summer at UCLA. So, language encoders in English have been widely deployed to facilitate NLP tasks. We have also witnessed the constant emergence of performant new variants, such as Elmo, Bert, Roberta, and so forth. Despite their differences in architecture or training strategy, the general pipeline can be interpreted like this. So, first, a language encoder is responsible for representing given data in a high-dimensional space. It captures the features and the relations of the inputs. Then, a task-specific predictor is trained to make the predictions according to the representations generated by the encoders. A basic assumption here is that both the training and the test data are in almost perfect English. So in contrast, we like to study the research question, how language encoders perform when confronted with grammatical errors from non-native speakers. Grammatical errors frequently occur in speaking and writing materials of non-native speakers, or they may also occur in user-generated content like web data. We leverage the data collected from grammatical error correction for English as second language learners to analyze language encoders. Here is an example on the column 14 shared task of grammatical error correction. These resources probably contain several parts. We may have an error tag which indicates the type of the error, and the original test which comes from essays from English learners, and also probably the corrections of original tests that usually comes from native speakers or English teachers. So what we do in this work is to systematically evaluate language encoders against grammatical errors. We intend to see how grammatical errors affect the model behavior, and from a different perspective, further understand if some grammatical structure is encoded in the models. Going back to the pipeline we have shown before, we envision to create grammatical errors on test data and see how much the model is affected. To perform this analysis, we need an automatic method to create ungrammatical tests. In the following, I will discuss our design of automatic simulation methods. This is in contrast to previous work, where they manually construct the new datasets as test data. We consider two scenarios, the average case and the worst case. For the average case, we conform to the real error distribution estimated from an English as second language learner's corpus. And for the worst case, we treat grammatical errors as adversarial attacks. The intuition is that the average case mimics a practical scenario, and the worst case identifies the brittleness of the models. I will first present the algorithms we used for grammatical error correction simulation, then demonstrate some experimental evaluations with our algorithms. Basically, we need two steps to simulate grammatical errors. First, we collect and mimic the error distribution from an available grammatical error correction corpus called NACL. The goal is to construct a pool of possible candidates so that in the second step, we can deploy some search algorithms to select from this pool and make token-level transformations on clean data. Let's move on to how to collect errors. Inspired by our previous work, suppose we have an English as second language learner's corpus at hand. We consider 8 frequent occur types in the corpus. They are listed in the table. These error types perturb target tests in terms of syntax, semantics, and both syntax and semantics. We hope that they will cover a wide range of grammatical errors an NLP model may encounter in practice. And then, for each type of errors, we build a confusion set. It generally looks like a metric like this. Each cell indicates the probability one word will be replaced by another. As an example, the top right cell tells that 73% of time, A will be added at a position where determiner is missed in the original data. Or we can say A is a correction of now. Then the confusion sets for other error types are more complex, and please see the paper for details. After that, we design 4 algorithms to inject the errors and create the test cases under the 2 scenarios mentioned before. For the average case analysis, we sample an error type based on the distribution estimated from the corpus, and randomly choose a plausible position to inject the error through the syntactic parse tree of the sentence. Then, we sample a word from the confusion metric and inject that error. For example, we might want to sample an article or a determiner error. A syntactic parser can help determine the positions of a noun or a noun phrase. Then we will know that we can inject an article here. So we can sample a word in the confusion set and substitute the original word with the sampled word. For the worst case analysis, we consider forming an adversarial attack to alter the model predictions by introducing grammatical errors to the input. The attack algorithm can be viewed as a search algorithm that checking all confusion sets for possible substitutions, then constructing an operation set to fool the model. We consider 3 search algorithms to select operations from operation sets. These algorithms are actually widely deployed in black box adversarial attack literature of NLP. There are greedy search attack, beam search attack, and genetic algorithm attack. Let's see an example of what we do with greedy search. Imagine we have a clean input test. It is of the quality of a lesser Harrison Ford movie, 6 Days, 7 Nights, maybe, or that Dire Fall Sabrina remake. We first rank each word by its importance. Actually, what we did is to delete words one at a time and measure its importance by the drop of model performance. Then, in the deepest order of importance, we try replacing each word with candidates from its operation set. This step goes iteratively, as we always practice the candidate that brings the largest performance drop. Such a method can be easily extended to beam search. Genetic algorithm is a population-based optimization algorithm. It doesn't need a ranking step, but requires gradually refining the attack samples. Please check our paper for more details again. Now we will come to the experiment. Our simulation method enables us to evaluate the robustness of models against the grammatical errors on downstream tasks. A few questions we can ask are language encoders robust against the perturbations? Which error types affect the models the most? And which downstream tasks are more sensitive? We can also construct probing tasks to investigate how models capture grammatical errors with context. Specifically, we take 4 widely applied pre-trained language encoders and evaluate on 4 downstream datasets from glue benchmark in a named entity recognition task. We also design some probing tasks, like a masked language model probing task for BERT, a binary linguistic acceptability task, and an error location prediction task. I will present the key results in the following, and please see our papers for details and other experiments. So, for downstream task evaluation, we inject errors to development sets of a target task and observe what percentage of predictions are changed. The big picture we observe here is that the robustness varies a lot among models, and it is also related to specific tasks. As shown in the 2 charts, 2 times of Elmo predictions are changed compared to Roberta. BERT's performance is in the paper, and it is between Elmo and Roberta. So in general, we found that Roberta is less sensitive to grammatical errors. We also intend to answer the question which error types affect the models the most. Here we represent their effect by the times they are chosen in successful greedy search attack. And we can observe from these 2 charts that the effects are similar regarding different tasks. Models are brittle to word choice and subject and verb agreement errors, and relatively robust to word order errors overall. And for masked language model probing task for BERT, we use BERT to predict some context words when grammatical errors are present, and measure the likelihood decrease of the proper prediction. In the top left heat map, we can see that, in general, specific positions get a greater decrease on likelihood. And our further case study on some error types show that the differences between positions might be related to the dependencies between words. A clear example is like this sentence in the page. When we change the determiner this, the head word group in the determiner non-dependency gets the largest likelihood decrease. To conclude, in this paper, we propose a new method to simulate grammatical errors. Considering real errors and search algorithms in adversarial text. Based on such a method, we perform a systematically evaluate and analyze the towards models. Our source code are available at GitHub. Thanks for listening.